try to make progress in this research area. And then all the opinions and the views are on my own, and it doesn't have to it doesn't reflect on the research that I'm coming from, and so there's also has to be taken okay. And of course, I try my best to say correctly pictures the historical events and also relevant citations, right? But then, so as you will see later on, because what I'm trying to go and talk about is like a standard typical is modern, I'd say, gate-based quantum computations, right? In the abstract, as you can see, there are also different types of quantum computing frameworks, and this is going to be a very, very difficult and challenging task. So that I apologize in advance that if I don't cite proper references or give a proper, say, citation to the necessary peoples and scientists, right? Apologies in advance, okay? Okay, and then also please remember to tune in Andreas and Thomson thoughts. Okay, they're going to talk about, say, Andreas is from computer science backgrounds, and Chuchin from the physics and chemistry background. So it's going to be also an interesting talk to listen to what they speak. Okay, right. Okay. So I guess that most of the people already say know this very big news, right, in the last year, which was like a big announcement in the 23rd of October 2019, right? And Google claims that their quantum processors can perform quantum computations, right? Which is like it took like 200 seconds or so, right? And for this kind of calculations to be done in the best supercomputer that we have right now, is going to be probably take about 10,000 years or so, right? And of course, this statement is a little bit of say, a little bit of exaggerating in a sense, but of course, and there are also many researchers trying to counter their arguments and also and so on forth. Okay, but I mean, for this thought, I'm not going to argue about what is true and what is right about these statements, right? So because this is clearly an excitement in the entire areas of the quantum computations, and of course, suppose that one day, if we achieve this kind of quantum advantage, right, this is going to be fantastic for humanity for overall, right? So that is no doubt is a exciting news and exciting development as well. Okay, and please take note that the Google machines, they only have like a 53 qubits, right, at the moment, right? And so later on, I will mention some of the numbers that you would like to make reference to these slides as well. Okay, so and very recently, in the again, this is not a scientific paper, right? It's just a news pop up like everywhere. Also, also in social medias, and of course, this is also again a very famous physicist from the University of Science and Technology of China in Shanghai, right? And he claimed to achieve this kind of a quantum advantage computations, right, which is 1,000,000 times better than the previous, say, the previous slides, right, the Google quantum computers, right? But I mean, we have not seen any scientific paper about this excitement at the moment. So, but this is really pretty exciting. Okay, and so. But again, in these recent developments, right, in my opinions, these are all, say, people are like looking into a particular directions of doing computations, right, which is very difficult to capture and simulate with existing classical computer, right? So, but in general, those kind of computations are not really useful in the sense that, I mean, these are the computations like in the case of Google quantum computer, what they're trying to do is like they're just running a random quantum circuits operations, right? And so there is no like a particular task that they want to do behind, right? So in the sense that these are not really a useful computations done at the moment, right? So, but of course, we know in the existing literatures, right? Like this has been already known for like for quite some time already, right? We have this very famous algorithms called approval search algorithms, right? And basically the task is, right, you have you're given a database. Basically, you have like a list of people with the names and like contact number or whatever it is, right? So and then you want to make a search to a particular persons, right, in this database, right? And of course, if your database is really large, then classically the most you have to do is like you have to go through the entire list of this database to search for this particular persons that you would like to search, right? So the notation here is this: you have this big O here notations, right? Here is basically saying that it's order of magnitudes, and if you have n entries of database, then probably in classical using the classical computers, and you have to search at least n entries to find this particular persons or entry that you would like to search, right? But in a quantum mechanical way, right, if you use a quantum computer, then the order of magnitudes is really now, you see that it is now square root of n, right? So basically, then you get like a quarter speed up in the computations, right? And as far as I know, we have done in the communities that was done for this kind of running this group of algorithms for the database with n equal to a search, right? And if anyone is interested in this experimental results, this is the paper that you should look at it. Okay. It was done in 2000, in the year 2000. And there's another known and very well-known and celebrating algorithms. It's called short factorizing algorithms, right? And here is the same thing, right? We would like to factor a number, a really large number, right? And this number, n, is a large number. And if we wanted to use a quantum computer, then you have exponential speed up, okay? So again, these are all really well-known algorithms. And again, today's talks, I'm not going to focus on those quantum algorithms and so to speak, right? So if any one of you are interested in this kind of algorithms, you can also look into this very interesting review article written by Ashley Montanero, right? This is a very nice article. You should look at it. And then I think Andrea's also going to talk about this, right? Mostly in this quantum algorithms, because his background is from the computer science. So I think you guys will learn a lot of stuff from his talk. Okay, so my background is in physics, so I will be mostly focused on how one can realize this kind of quantum computers in the physical settings and actual physical hardware. Okay, so let's set the stage. Okay, so I guess that everybody is familiar with this kind of classical computations, right? Well, we use, say, electrical voltages to represent our classical bits, right? And 0 and 1, right? 0 means 0 volt, and 1 means like a voltage of about 3 to 5 volts, depending on the architecture that you use, and so on and so forth, right? And so you can generate this kind of voltages with oscilloscopes, and I don't have to go into details. And of course, I mean, in this classical computing, we will have a set of logic gates, and I'm not going to go into those details, right? The main message here is that, right, these different types of, by making use of these different types of logic gate, one can actually design different types of classical algorithms, right? And that's a point of classical computations, right? And here in this little box here, I have mentioned here is that the NOT gates and the AND gates, they form a universal gate set, right? The notion here is that what I meant by universal is that by making use of this NOT and AND gate, one can actually reproduce any other logic gates that you see here, right? The same apply to NAND gate. So by a collection of a NAND gate, you can, in principle, reproduce those logic gates as well. And as well as that's true for NOR gate as well. So that's why these three set of gates are called universal gate sets. Okay, so I'd like to take notes of these notations here because we are going to make use of this in the quantum computations as well. Okay, so but again, there is sort of like I would say bias or what do you call it? In a sense that classical computation is not basically based in the electrical circuits, okay? What I mean by this is that, 0 and 1 can be anything, okay? It's not necessary that we have to use the electrical voltages, right? As long as we can reproduce those logic gates in a proper way, one can, in principle, do any types of classical computations, right? So I would like to give you 2 examples, okay? So this is again, as I mentioned in earlier, right, this is going to be a biased opinions and it's going to be also a subjective, right? So this is a recent paper from our lab as well, and here say my colleagues they propose to use molecular droplets to perform classical computations, basically, right? And so they define 0 and 1 to be their molecular droplets, okay, and the colors of the molecular droplets, and then you can do some sort of optimizations, algorithms, and so on and so forth. Okay, so so the same applies here in the second example. This is just a coffee stain, right? And so I can also use a coffee stain to define my classical big 0 and 1, and then one can in principle perform classical computations, and that's not a problem at all. Okay, so this is I would like to move on to then generalize to quantum realms, where quantum business has a little bit strange behavior, as I mentioned earlier on, right? In classical big, where you have 0 and 1, and then of course you have a voltage of 3 and 5 volts, right? But again, this 3 and 5 volts is just an arbitrary setting that we choose, right? But in principle, this is a kind of like a continuance of voltages that one can apply, and so the distinctions with quantum realm is that in quantum setup, basically if you take natural atoms or say sodium or rubidium atoms, and if you look at the hyperfine states structures, right, and the level of separations are already predetermined, and they come in with discrete energy spectrums. Okay, so that's a concept of quantum being like a quantized notions of the energy in this way, right? And then the notation here is that, okay, we have state 0 written with this vertical line with the right angle brackets and a 1 in a similar fashions, right? And of course, I'm showing you here is different types of, in these pictures, right, different types of lasers, right, with different colors coming up. So the reason that you have different types of colors coming up is basically is that the energy separations are now different to different types of lasers, and basically they are using different types of elements inside. So that's why you see different types of colors that you see. Okay, and this kind of quantized energy is also seen in the typical electronics watches, right? If you if you if you have a electronic watch at home, right, and you flip the back of the watch and have a look at that, and you probably sometimes see like Japanese movements, and you say quartz crystals or something like that, right? And that's basically is that we are probably making use of this. We are making use of this quantum mechanical properties of this crystal vibrations, right? These are also coming with quantized vibrational modes. And what happened is that the electronic circuits were taking notes of these crystal vibrations, and the second is defined with like how many vibrations that being made in this crystal were defined as 1 second intervals, right? That is how the electronics watches are recording times, right? Dailies, and so. A little bit of a theory here is that back in 1900s, right, Max Planck, basically, as you can see here in this formula, H is basically is a Planck constant, and to honors the inventors of this quantum theory back in 1900s, and basically he invented this just to explain black body radiations. Okay, but again, I don't want to go into those details because this is going to be a general public talks. And so again, in 1905, Albert Einstein used his theory to propose a photoelectric effect, and then because of this, he got a Nobel Prize, right? And the photons was named in 1926, and the famous Schrödinger equations and was invented by Schrödinger in 1926, right? Is to study the evolution of the quantum mechanical systems, basically, right? And once you solve this Schrödinger equations, you can basically know everything that you would like to find out about this quantum mechanical systems, right? And this is a picture was taken in 1927, right? This is a very famous conference called Seoul-based conference, right? And only I mean, not everybody can attend this conference. It's only via the invitations, and then you see here in the pictures, right? There are so many famous people. Most of them are the founders of this quantum mechanical theories. Okay, and that's how the beginnings of this quantum physics quantum era started in 1927, right? And surprisingly, after 120 years, right, now we have IBNQ System 1, right? Basically, now anyone with a huge amount of money, then you can buy this quantum computer if you want, right? And also if you like to manipulate quantum systems, right? You can do so online via the internet, right? And I mean, you can register at the IBM websites, and you can start playing around, and you can do codings and try to play around with the quantum circuits and so on and so forth, right? So I mean, this is fantastic developments, right? I mean, our quantum mechanics founding fathers and mothers were never vision to be that we will be able to control and manipulate those quantum mechanical systems via remotely on the internet, right? That's amazing progress that we made. And this is going to be a prelude to my second talk, which is going to be next week at the same time on the same day, Thursday. And as I mentioned before, in classical computers, right, one can define classical bit 0, 1 to be say you can take a coffee stain or electrical voltages or molecular droplets, right? As a similar fashions in quantum realms, we can also have different types of physical setup, right? Those are, I have listed a few popular design and say architectures here. Here is a superconducting circuit, and we will have linear quantum optics set up, right? And also we have NV centers, and we have trap ions, and then we also have a quantum dots, right? Again, I mean, sometimes probably you will be familiar with this notion of quantum dots because I think Samsung has televisions, right, made with quantum dots, right? And probably some of you already familiar or have it at home already. And but again, this is I mean, we would like to manipulate those individuals quantum systems that will performs quantum logic gate operations, right? So and let me quickly go through this. I think probably some of you are already familiar with those notions of quantum superpositions, right? And is that, I mean, like we have, I mean, people, I mean, in the popular cultures, we have this cat being dead and alive, and also, you know, like simply because of the fact that we have quantum state, which is a wave functions, and the wave functions. Now we see the 0, 1, right? The notations are given here. And these wave functions can be in an arbitrary superposition of this state 0, 1, right? That's a different and a clear distinctions that we go away from the classical computational realms, right? In a classical computers, we don't have this kind of property, weird and strange properties, and also this is the properties that we use in the say Shor's and the Grover search algorithms as well, right? And in here, what I'm showing here is a sphere. We call it a Bloch sphere. It's a three-dimensional sphere to represent a state of this qubit quantum bit, right? And the north pole is denoted as a state 0, and then the south pole is denoted as state 1 here, right? And so a quantum state can be in on the surface of any place on the surface of the sphere, as well as inside the sphere. Okay, but again, I think most of you are probably familiar with like a state being on the outside of the I mean, not on the surface of the Bloch sphere, but I mean, if quantum state going through say decaying, then the state is going to be a string and it's going to be inside the sphere. But again, this is a little bit technical, but what you can see here is that, okay, so I can now parameterize my quantum state with respect to Taylor's and phi, and so because basically this is how you define a state, right? And the notions of the state that can be dead and alive is that basically because we don't know, even though, right, the quantum state is in a superpositions, right? We don't really know what a quantum state is, right? Unless we make a measurement, right? So this is purely quantum mechanical properties. And so we have to, in a way, we have to, in a lab, we have to initialize the quantum state many, many times and make a measurements many times and get the statistics. And then from there, we can sort of construct the statistics and start to see what is the state of actual quantum state. Okay, so that is there's a notions of a cat being dead and alive at the same time. Okay, another very strange properties of quantum mechanics is the nothing but the entanglements. Okay, and so here, instead of explaining what is quantum entanglements, I will tell you how to make entanglements. Okay, so that in a way it's kind of a very strange properties, and I mean, until now, there are so many arguments and many of the philosophies of philosophical science are also trying wondering about what is the interpretations of those kind of entanglements and quantum properties, right? There's like a sort of like a notion of whether there is a physical realisms or determinisms and localities and all those stuff are coming out with this entanglements entangled states. Okay, but we don't want to go into those details at the moment. Okay, so how typically in the lab we try to generate this kind of entangled state is like as you can see in this picture here, right? We have like a laser. So basically here in this example, we have a UV laser, so very high power laser. This laser coming up and it's passing through this BBO crystal. And so this crystal is a nonlinear crystals, and the job of this crystal is that, okay, once it's coming up, right, it takes this incoming laser, and due to the energy conservations and momentum conservations, you will see two conical cones coming out, right, because of the scatterings effects and all those stuff, right? And so here, so if you look at this cross section here, right, in this picture here, right, in these two junctions here, right, you have the blue ones and the red one, right? If you look at these two positions, right, what you see here is this quantum mechanical state that I have written down here. Okay, so you have H means horizontal polarizations and V means vertical polarizations. Okay, don't worry too much about the technical terminologies. Okay, you can think of this like H being zeros and V being 1, right? That I defined earlier on as well, right? So then basically here is that, right? And of course I also written down a typical four different pair states, right? These are the highly entangled states, and so this state is here is nothing but the state here, right? But of course, forget about this phase factor. Yeah, but we're gonna take phase to be zeros, and we'll give you 1. But what you have is a 0, 1 plus 1, 0, right? And of course, A and B being subscripts written as like A is a notation of like a site position 1, and B will be in a position 2, right? And so if you look at this carefully here, right, you see that at any point in time, if you make a measurements to this quantum state here, so because if you make a measurements, you will project it into either of these states, right? Either in this state or in this state, right? So then you will end up with 0, 1 or 1, 0 state, right? So it's like half, 50% probability always end up with like if it is positions 1, if you have a 0, then in position 2 you will have a state 1, right? And if you measure position 1 state being a 1, then you know that at the position 2 you have a state 0. Okay, so that is basically is a properties of quantum entanglements, and this is a entangled states. Okay. So anyway, if you do have questions or anything like that, I think you are allowed to ask questions, or you can also type in questions in the chat as well, whatever you like. Okay, let me move forward. So let me go into details about a little bit of the going through these quantum gates. And okay, because as I mentioned, in the classical computations, we also have different types of logic gates, and in the quantum realms, we also have different types of quantum logic gates, right? And here, and corresponding actions on this block spheres states that you have here, right? So identity means is just doing nothing, right? X means like you rotate along the x-axis, right, 180 degree, right? And a 1K being a rotation of 180 degrees along one axis, right? This is X, Y, Z axis on a block sphere, right? And similarly, we do have so different types of gates like Z gate, S gate, T gate, and Hadamard gate, right? So say for instance, Hadamard is a very, very important gate, and you see here, right? What it does is that it rotates in the XZ plane. On the AC plane, you rotate 180 degree. Okay. So if you have any quantum state, right, then if you apply this Hadamard gate, then it will rotate that quantum state in these fashions. Okay. And if any one of you are interested in the details of like you know, very in-depth stuff, I think I recommend that you see this review articles as well. And then similarly, we also have two-body gates, or basically it's entangling gate, right? We have a CNOR gate and also control phase gate operations here, right? The action of CNOR is nothing but, you see here, right? The notation is here. The line coming up here is each line represents a single qubit, right? So we have a 2 qubit. That's why we have 2 lines. Here we have the ball circles represent a control, and you have a target operations, target qubits and control qubits, right? And so the action is nothing but, if you have a control in a control qubit, if it is 0, it doesn't do anything, right? If the control is 1, then you will flip the target qubit to from 0 to 1 or 1 to 0, right? So basically that is the job of a CNOR gate. And CV gates is nothing but, it's the same thing, but in a sense, it's the same thing in the sense that you apply the control and target, right? But the action is that you will add a phase, extra phase minus here, right? And again, here in the quantum computations, we also have 2 different sets of universal quantum gates, right? So one set means that it's an arbitrary single qubit gate and a CNOR gate, right? If you can perform these operations in your quantum mechanical architecture setup, a physical setup, right? Then basically you can do any types of quantum algorithms. You can run any types of quantum routines, right, as you wish. This is possible because of this universality property, right? Similarly, we also have a different set, which is a HST and CNOR. Basically, it's a T gate, what we call in the literature is called T gate with it's a collection of Toffoli gates. Okay. And again, with this set, basically, then this is the already the end of the what we all know as a typical say gate-based quantum computation approach, right? Because I mean this is what you mostly probably is some of you are already familiar with this kind of gate-based approaches, and you can write down any types of say algorithms in terms of this kind of single qubit gates and 2 qubit gates operations, right? So, but let me bring you attention, right? Why is this making a quantum computer so hard, right? Simply because that because we already know, right, everything's right. Quantum computer is so good, right? It gives a potentially exponential speed up to the classical quantum computer, right? And also, we know all the universal set of quantum gates operations, right? Then how come that until now we are not having a practical quantum computers that we can use daily, right? The reason being is as follows. Okay, here I'm sure. I'm sure the people. Everybody's familiar with these Matrix movies, right? And here, Keanu Reeves, right, being Neo's, right, he can move super fast, right? As you can see here, right, he can basically deviate away from all the bullets, and also he can also stop bullets from coming into hitting him, right? And as I chat yesterday, right, online, typically a pistol from a bullet is about say 350 to 564 meters per second, right? But of course, if we talk about semi-automatic rifles and other things, it's much faster. Okay, but as you know that air particles in the air, say waters or some random particles in the air, right? At the typical room temperatures, we have about 300 to 400 meters per second or so, right? Based on the say thermodynamic estimate, right? That is basically is order of a speed of a bullet, right? Basically, and then I would like to tell you that we physicists are super cool, right? We don't rely on, like in this movie, we don't rely on CG computer graphics, right? We really stop the bullets, and that is clearly seen in this picture here. Okay, this is a very interesting experiment that people done in I think quite some time ago, and here is a picture of Bose-Einstein condensates and three different screenshots. And what you do is that in order to achieve this Bose-Einstein condensate, one wants to heat up the say typically we will use like rubidiums, potassium, or so whatever like natural atoms. I think they have a preference of like what kinds of atoms to choose based on their hyperfine splittings and others, right? But anyway, the point here is that, right, in order to choose this, right, one has to heat up those natural atoms, and typically it is much faster than this bullets, and then one has to stop those atoms and make it stationaries, and then cool it down, going through different types of stat, right? Kind of laser coolings and trappings and evaporative coolings and all that stuff, right? Afterwards, then you arrive to like coming from, you see, 400 nanokelvins, right? And then coming and arrive to nanokelvins and 50 nanokelvins, right? And then you see this is a velocity distributions, and basically these are all like quite stationary. Yeah. And this is amazing. And then I think any one of you interested in this topics, I will recommend this incredible textbook by Markov and Van der Straatens. Anyway, so yeah, because of this amazing achievements, right? So as you know, probably Stephen Chu is like Obama scientific advisors, right? I think the first one, Obama was one of the first times he was the scientific advisor to the presidents of the United States, and then together with Kyaw and Bear Phillips, they got a Nobel Prize in 1997 simply because they invented this technique called laser coolings and trapping techniques. Okay, and based on this laser coolings trappings, right, and Eric Connors, Carl Wyman's, and the Wolfgang Catalyst, so basically this picture is coming from the Eric Connors lab in Jilla in the University of Boulder, right? They made this beautiful experiments, and because of that, they got the Nobel Prize in 2001, right? And recently, right, quite recently, so Sergio Haroche in France and Dave Wylans again back in Nice as well. So they got a Nobel Prize simply because they use this kind of trapping techniques to manipulate individuals' atoms to perform quantum computations onto those ions and natural atoms, right? In very high precisions. Okay, so but again, the difficulty lies in the fact that, okay, so I mean, I'm just showing you that we have gone a very long way, right? I mean, physicists, we being physicists, I mean, super impressive, like stopping bullets, right, to controlling individual atoms, right? But again, the difficulty lies in the fact that if we are trying to scale up those individual quantum particles, we really have problems, and so there are so many challenges, and the noises are also coming in play, and there's challenges that we are facing nowadays at the moment. Okay, so with that, I would like to tell you a little bit about like a killer apps, right? I think with the remaining 5 to 10 minutes or so, right? And so, of course, in the communities nowadays, we've been thinking about like what is the killer quantum applications, right, to take advantages of this incredible controls and properties of the quantum natures. One say leading direction is in simulating chemical molecular systems, right? So let me try to give you a very recent article. This is an article which is not published yet, right? This is appear on this archive preprints, right? Dated 9th of November, right? So it's a few days ago only, right? This is coming from Google Quantum AI, and also Nathan Weeb, who is coming to U of T as assistant professor, I think in January 2021 as well. I think he's going to be affiliated both in the computer science and the physics departments, right? So those are the, I mean, they are the pioneers in the fields, and they predicted the following things, right? Okay, here they took this very interesting chemical processes called nitrogenation genesis processes, right? Which is, I don't really know and familiar, but you have a look at this, the FeMoCO cofactors, and this is very important, right? And of course, in order to simulate this kind of processes, right? And then they say is that, okay, they have already optimized the best possible way in the literatures, right? And even then, in order to simulate those kind of processes, we will eventually need about 4 million physical qubits, right? Right, this is the highlighted test here, right? You have a look here, and probably the runtime of a quantum computer is about 4 days or so, right? In order to run and do this kind of impressive calculations, right? And then in the beginnings I mentioned, right, we have 52 qubits at the moment in the Google quantum processor, right? So as I mentioned, we have a very long way to go. Okay, and at the same time, we have to be open-minded and not really mainly focus on, say, typically one types of processes or quantum computer framework, which is a gate-based, right? Mostly people are talking about this, and then I would think that many different types of frameworks are also worth attentions. And with that, right, with the remaining 5 minutes or so, I will try to give you a hand-waving arguments of what are these different types of quantum computing frameworks, right? Because being a general public talk, I can't go into a very technical terminologies, and these are all very technical, and you need a lot of mathematical understandings and all those stuff, and so but don't worry too much. I will try to explain what are these, and so the first is the measurement-based quantum computations, right? So it is similar to playing like a chess game, right? So in a chess game, what we need is two things, only two things, right? One is being a chessboard, another one is different types of chess pieces, right? And of course, if I'm going to give you a chess pieces and without giving you a board, you can't play on it, right? Because you don't know how to move, right? And at the same time, if I want to give you a chess board and not a chess pieces, then you can also make a move as well, right? So we need both, right? Here in the MBQC, what we need is two different things as well. It's called cluster state and local measurements. This is very similar to playing a chess game here. So here in this picture here, so again, these are all mathematical constraints, and I am not even talking about physical realizations, right? So just go along. Okay, so we need a cluster state to do this kind of a measurement-based quantum computation, and this is different from the gate-based computation in the sense the following, right? Here, now, in each circle, we will need we will have to initialize in a plus state, which is a superposition of 0 and 1, right? And then you have a bond each bond will require a control phase gate operation, so which I already mentioned earlier on, right? And so the point being here is that before you even do computations, you need to prepare this kind of a checkerboard resource states hand, right? Once you arrive and have this resource state, what you have to do is that from left to the right, what you do is that you make a local measurements. Okay, don't worry too much about what is local measurements. Maybe you can also ask me later on, but basically you make a projective measurements, and depending on how you make a projective measurements, right? Here in this example, right, you just measure 5 different blocks, and in here in this 2-dimensional plot, you can realize a general 1-qubit rotational gates. Okay. And similarly, of course, X, Y, and all those notations being the Ace gate and 1 gate that I mentioned earlier on. Okay, here you have this realization of C0 gate, right? As you mentioned earlier, I told you before, there's a universal gate set operations, which is a C0 and a general 1-qubit rotations, right? So this with these two, you can realize a universal quantum computation, right? Here, also in these fashions, you can realize a C0 gate operations, right? So basically, it's a chess game, actually, right? And then, so my understanding here is that in this community, there is not many issues about making measurements. Most issues are in the case of preparing this kind of cluster state, because we don't really want to go in and do the gate-based approach and like individually prepare qubits and prepare in a plus state and perform a C-phase gate operations in between, right? That is a waste of resources. We would like to have a scenario where we take a quantum systems and we cool it down to a ground state. Basically, is that we switch off the temperatures, right, and cool it down to the minimal energy state. And once we arrive to the energy state, we achieve the cluster state. So this is like a few years back ago, we make a proposals where we show that we can prepare some sort of a cluster states again, there are a lot of technicalities, and I don't want to go into the details. But again, here, so if it is in here in the 1D, you can only realize the single qubit gate operations, right? So it's not a general. So if you want universal computations, then you need to prepare this kind of resource states, and then if you want to involve fault-tolerant quantum computations, then one have to go into this kind of a model operations, right? But again, this is still mathematical modelings and theoretical proposals, and there are still a lot of experimental challenges remains. Okay. And with this, I would like to move on to discuss about holonomic quantum computations. Okay, holonomic quantum computation is like, it is very, very, in my opinion, is also very cool as well, in a sense that here, it is akin to like going through a McDonald's drive-through here in this picture here. Okay, let me explain a little bit what I meant. Yeah, what I have is the we have, we have the initial ordering stations, right? And it's a blue dot, and the red one will be the end path, right, where you collect your parcel, right, your orders, right? Basically, and then you just go in and you drive through, and of course you see there's a typical pathway already defined for you, right? But of course, here, right? But then suppose that you just pass through here, and then you wanted to like make a funny move, right? And then you can go to some of those parking driveway, and you can park here, and then you go some other directions, and then you go around and take your U-turns and back and forth, right? And then but finally, you have to go through this red color dot to take away your parcel, right? The order. But again, here's the thing, right?
Yeah, I just want to interrupt. So, all great content. I think we're 5 minutes past the talk time, though. We want to go into Q&A, and we don't want to take up any time. So, there's a second sessions for the same topic. So we'll probably move to content. To
yes, it's great interest. So, but I will try to finish then. Okay, so I can try to stop here. Okay. Also, what we can do is that we can push everything into the Q&A session as well. Okay. Let me try to end this by saying that okay, I have the target is that I would like to introduce different types of quantum computing frameworks and how to realize that in the hardware, right? The real hardware and what is the mechanism behind those hardware. And so my second talk is going to be mostly focusing on the quantum hardware, realizing these different types of quantum computing frameworks, and we will need like a young undergraduate student like you, right, to study physics and the majors in this quantum computation to make a major breakthroughs, right? And with that, I will end and give acknowledgements. And this is our lab. I think last year before the pandemic happens. And yeah, with that, thank you very much for your attentions. And if you have any questions, I will take from here.
All right, thank you so much. I think there is actually questions from the audience, I think, regarding slide, I think 19 or 18 on the universal gate. So I think if you were to read the chat, I think people are confused about, I think, 19, slide 19 then. So what's the difference between G1 and G1 and G naught, and what is P theta?
Right. Okay. It's a very good question. So as you see here, P theta I have defined here, right? It is just phase factors in front of the identity matrix. So it's just extra phase. Does it answer the question? Hi. Any response? So basically, the point being, yeah.
Okay, that sounds great. We have another question. Do qubits from Ernest Crack? Do qubits need to be entangled to be used in quantum computing?
Can you repeat the question again?
Okay, so we have a question from Ernest Crack. Do qubits need to be entangled to be used in quantum computing?
Right. Yes. This is depends on the algorithms and that you use, right? And so as I mentioned already here, so again, you can answer these questions from this slide as well, right? So basically, you can think of it as say control phase gate is like control phase, and signal gate is kind of like entangling operations gates, right? And so one to answer is that yes, again, it depends on your algorithms you want, but as you see here, in order to have universal gates, logical gate operations, right, we would like to have this kind of entangled gates as well. And another answer is the following. I mentioned about this measurement-based quantum computations, right? So here in this measurement-based, this is similar things that you see previously, right? The universal gate set that you seen earlier on. So the answer to that is also here, right? The general one qubit rotation, right? That is a G0 set and the signal gate, right? And that will give you a G0. And as I mentioned earlier, the the resource for this measurement-based quantum computation is a cluster state. A cluster state is in the literatures we call it a highly entangled state, right? So basically, all the qubits that you see here are supposed to be entangled, and then once you have that, then you arrive to the cluster state, which is a resource state for this measurement-based quantum computation. Is there any other questions?
Yeah, I think we had a question from early on, just to clarify things as to what constitute a local measurement.
Ah, right. You mean what is the local measurement? Am I right?
I believe that was the.
Yeah. So this is the local measurements being basically is because you have like say like two-dimensional qubits, right, so to speak, and so I can label those qubits as like a qubit 1, qubit 2, qubit 3, and so on and so forth, right? So then I have to make measurements individually, right? If suppose that if I want to perform, say, the general 1 qubit rotations like I show here, right? Then if I have this resource state here, and then of course in principle, I can use the first row, right? And when I have local measurement means that after preparing this cluster state, now I have to make a measurements in this qubit. What measurement is X operators, right? As you see here, X, right? So basically it's you perform X gate operations onto this qubit here, right? Followed by other gate operations that you see here as well. So that is the local measurements. A global being is a collection of entire things, is a global, right?
Okay, thank you. So so our time is up, but we're I think Thiha is also willing to stay here for further questions. So there's actually a lot of people asking you about your about the Matter Lab and you know quantum chemistry. So if you just could check the chat, there are so yeah, so we'll just be a bit free form now, just having discussion. So no formal Q&A questions sessions now. We're just purely chatting, starting now. But yeah. So yeah, could you could just go on check and check the chat.
Right. All right.
So I think we got someone asking about your research, Kyaw.
Yeah, I think there's a person. There was a Aaron, right? I think he asked like, what is the significance of the pi by 2 pause? So it's a question. I'd like to know more about coffee stain computing. Right. So I think for that one, so if you would like to know more about that, I will advise to look at this paper. Again, I mean, these are all very similar idea. So I think if people are interested, this is I mean, completely available online, freely available. This is a chemical archive, right? So if you would type in Google, the title of the paper, you should be able to read through what it's all about. So I'm not so familiar with those, so I can't answer beyond this point. And okay, there was this pi by 2 pause, right? I believe this has to do with this one, right? Okay. So basically, yes, I also rush through, and yeah, it's also difficulties, right? I don't know how much of you know the backgrounds, and it's hard to judge. And so I think I did not explain what is pi by 2 pause. Basically, in these blood sphere representations, if you would like to achieve like Schrodinger cat state, right? I mean, like this kind of being a state in being a dead and alive, or dead or alive state, right? Basically, then you have to apply this pi/2 pulse, right? But again, I will talk a little bit more about those in the next sessions. If you come listen next week, like in a real physical setup, what does it mean by the pi/2 pulse? But the terminology here is that pi/2 means because you are rotating your state from state 0, right, going into the equators, right? So there is a 90-degree angle sustained here, right? So that is the essence of a pi/2 pulse, and if you apply that, because normally when we initialize a quantum system, we will start from the 0 state, right? Because that is easiest to prepare, right? Because it's in the ground state, and as you can see also from the picture here, right? It's easy to prepare because one, if you know a little bit about the physics background, if you prepare in one state, it will decay here. It will decay, right, because of the spontaneous emissions, right? So basically, state 0 is prepared easily and can be prepared easily, and normally you cool down your systems to lowest temperatures, and you get the 0 state, right? And then what you do is that now you apply either depending on your physical setup, right? Can be a quantum optics setup, or can be say a microwave or optical pulses, right? So you apply this some sort of excitations, and that will go into a superposition of 0 and 1. So there's a significant, there's an addition of a pi/2 pulse. Okay, yes. Okay. Someone is was a complete out of phase. Okay, anyway. Is there any other questions, like technical question? Right. Zoom quickly. Us. Right. Okay. There was a Ernest Prack. There was a question about frequency. Frequency and in the Hz. If you would like to ask, you can also ask again. I don't really take questions.
All right, so I think that will be it for the day, more or less. So if you want to ask Tiha more questions, so please just email him. So maybe you can copy and paste your email at the chat for people who didn't note it down at the very beginning. But yeah, I think so. Thank you for everybody's time. Your involvement is definitely much appreciated. But yeah, so I think that will be it for the day. So thank you so much, and have a very wonderful evening. We'll see you on the next event. So that is next Monday. All right. See you everybody.